How's it, everyone? So I'm going to give a brief presentation just about the mathematics behind relational database, because like a lot of stuff in computer science, but in particular for relational databases, there's quite a strong mathematical basis to it all. So most of it comes from a paper written in 1970 by E.F. Codd, and it's actually very readable, surprisingly, and it's quite interesting. So I'll just start off with a set. A set is just a mathematical object that can contain anything, but it also can't have any duplicates, and the order of the elements doesn't matter. So here's an example of a set. It contains a pair of scissors and the number 1. So it can really just have anything. But a more useful set would be something like the natural numbers, starting at 0 as God intended. But on top of that, now we have the Cartesian product. So the Cartesian product will give you all the pairs possible to make from two sets. So for example, we have a set of colors, red and green, and a set of shapes, spheres and hearts. And then the Cartesian product will get the set of all colored shapes. So we can have the red circles and the green hearts and everything. Every possible combination. Importantly, the order does matter in this case. If you had a circle and then a red color, that would be a different thing. We can repeat this operation as many times as we need. So for example, now we have big or small as well for the shapes and colors to have even larger amounts of information. So relations now. Now I'm strictly talking now in terms of mathematical relations, which are very much related to relations in a relational database, where a relation is a table. But it has a very simple formal definition. If you have now your colored shapes set, and we just remove some of them, so we only have some. That was called a subset. We have a subset of the colored shapes, which we call R. And that is a relation. A relation is just simply defined as a subset of Cartesian product. So yeah, we have this relation R. We could call it anything. We've associated red with hearts and green with circles. So we might write this out like this. We have red heart is in R, or red is related to heart by R. And we also can say, okay, R is the typical color relation. So red is a typical color of heart. Often now you have the relation less than would contain all the pairs so that the first number is less than the second number. So that's where the word relation comes from. It's about less than, or you have equality relation, which would contain all the pairs where the first number and the second number are equal. So we can now just show this as a table for more convenience sake. And it's starting to look a bit more familiar now because this is just, a table in the relational database. But we need a bit more. But let me just go summarize. So you have set containing some amount of items. Then you have a Cartesian product where you construct pairs from all those items. And then relations where you only choose some of them. You don't just go with all of them. So in a sense, the Cartesian product is all your possible items that you could have in your database, in a table, sorry. And then the relation itself is only those items which you actually have. But you need more than just relations. You need constraints because, for example, you have these two databases, these two tables or relations. You have employee, which has all these employee IDs, and office, which has only office IDs. And of course, the IDs are natural numbers. So now we introduce R, which is maybe called employee office or something, and it just has a pair where the first is the employee ID and the second is the office number. So we now have some constraints because R is just a subset of n cross n. So it's all possible pairs of natural numbers, but That's useless because we could have an employee that doesn't exist being in an office that does exist, or an office that doesn't exist going to an employee that does exist. So we need to have some way of ensuring that this is still valid. It still doesn't contain invalid data. So we have constraints. So this would be an example of a foreign key constraint. Each employee office must exist in employees, and each office must exist in office. And we can have that no two employees share the same office. And a constraint is just simply any true or false statement about the database at a point in time. So it could be like the ones before, or all office numbers must be 3 digits starting with 1. It's any statement that you can say at a point in time, is this true or is this false? So if we go back to employee and office, and then we have our employee office relation, we can have a constraints here to ensure that employee and office is like that. But this can be a bit of a problem because, like I said earlier, constraint can be any true or false statement, but it could also be something that's, extremely difficult to compute. So, for example, even a simple thing like a uniqueness constraint, employee office must be unique. It's easy to check when you're adding a new employee office link that, okay, this office is already taken or it's not. But it must be true at a point in time. So you should be able to go back in time and say, if was this state valid here or whatever. It's a product of the database itself, not of a change to the database. So you won't know necessarily in the relational model whether or not a change has occurred. All you know is the first state and the second state, after the change and before the change. So you lose that information about which office was just added. So it can be very expensive now to check. It's rather than saying, oh, I'm adding an office 104, does it exist already? You're going through and saying, okay, all these office numbers, are there duplicates in it? Which is much more expensive to check. But I'll come back to that later. So we'll go over the selection operation. So it's defined like this. You have pi, it's called, and then you have a list of numbers, and then the relation that you're operating on. It's just a function. So yeah, you have employee office, and salary, and then you have selection of column 2 and column 1 for which will select out the offices and the employee IDs, or you can repeat them to have column 1 and then column 2 twice if you wanted for some reason, or column 1 and 3, and this is equivalent to this in SQL. So it's just your select, but it's importantly, it's this part of the select that's before from. It's just the columns that you're selecting. It's nothing to do with anything else. Then we have the restriction operation. So just like you can have a function f, which squares a real number, but then you can restrict it to only operate on natural numbers. So that's written like this. And now you can see f can only operate on f, line n can only operate on natural numbers, can only square natural numbers. Just like that, we can do the same thing for relations. So we have employee here, and there's another relation now we've introduced now, which is called the special offices, called S. So we can restrict employee by special offices. And now we get only employees that have a special office. And that's written like this, because we're taking column 2, which is office, restricting on column 1 of special offices. And that's equivalent to this SQL statement, which is not actually a built, it looks a bit funny in SQL because it's not a kind of a built-in feature of SQL. So it's interesting that we lost that in between the 70s and the present. But in terms of practical implementation, say we have it's the same relations as earlier, but in particular this one. When we're adding a relation, like I said earlier, it's easy to check, but it can be slow to check for all of them. But constraints must be able to be checked at a single point in time. So we don't have to keep a record of all the changes that were made. We only have to know at a point in time how it was. So if we have our database here, it's made of the database, which is made of employees, offices, whatever, and these are the rows, and we're adding office number 102. And we're now just checking a constraint on a single row. So this is that it's 3 digits starting with 1. So it's more than 99 and less than 200. This is actually quite trivial to check, because if you're adding a single row and the constraint is function of that only row, all you have to do is just check that row. So in a check constraint in SQL, you can't go and check anything else outside of the particular row you're working on right now. So that's why in SQL you're allowed to do anything in a check constraint, as long as it's only a function of that row. But now if we're doing something a little more complicated, like a uniqueness constraint, we have to, remember, we define it in terms of checking the database as a state in itself, not as in a change. And this can be quite expensive, because you have to go and loop over all the offices, get the count of each of the offices in this pseudocode example. This will take a O(n) squared time, if you're familiar with that. There is a solution, and that's just to kind of break a bit from the relational model. And now, instead of expressing a constraint as a point in time, it's now expressed as a change, where you have the existing offices and a new office. Now it's just quite trivial. It's just checking one office. If it's already present, then okay, good, we can add it. But that's not always sufficient. So also, this can be quite complicated to force logic to be stated in this way. This example, it is actually simpler, but that's why in a lot of SQL databases, you can't just express arbitrary constraints over the entire table. You restrict it to a certain number of constraints. You restrict it to a foreign key constraint or uniqueness constraint. You can't just put whatever. So here's an example for accounting. We're requiring that in this accounting database, all the debits equals all the credits. This is quite easy to express as a function of all the accounts, but it can be a little bit more difficult to express as a change, because if you're adding a new account at the same time, in the same transaction, you're transferring from one account to another, it can very quickly become complex. There's like 100, I'm exaggerating, but there's a lot of different cases you have to check in order to ensure that the database remains balanced. Anyway, that's basically the maths just behind relational database, if anyone's any questions. Also, somebody was driven mad by the Wikipedia article on this and started going on about criminals have taken over the Wikipedia page, which is quite interesting. So I'm not quite sure what that was about. But apparently Hell's Angels have taken over the relational model.